right, let's try this out. This is Functions and Relations, Lesson 7, the Part 2 lesson to the inverse of the relation, and the very last lesson in this first unit. So yesterday we established a couple things. We said when we're looking at the inverse of a function, if you have a set of ordered pairs, x, y are getting switched and they're becoming the ordered pairs yx. We also said that graphically, if you look at the graph of a function and then you look at its inverse, it appears to be reflected over the line y equals x, which we also call the mirror line. And if we were solving for the equation of a relation algebraically, we would interchange x and y and solve for y. And we noticed that a couple interesting things happen when we do that. The domain of our inverse happens to be the range of our original function, that meaning the domain and the range are switched. And the same goes for the range of the inverse now becomes the domain of the original function. So again there, the domain of the original was switched and it becomes the range of the inverse. Now, the inverse of a function may or may not be a function. The easiest way to test that is with the vertical line test, where you drag any vertical line, including a pencil, across the page and you're checking that it only crosses through your function once. If it crosses twice, it's just a relation and not special like a function. So consider the relation x minus 3 squared plus y squared equals 9, whose graph is a circle, center 3, 0, and radius 3. So it helps that they told me what the shape was, where it's centered, and its radius, because otherwise we would have a lot of difficulty graphing this. So we're going to put a center at 3, 0, oops, right here, and radius 3. So we're going to draw a radius of 3 all around here. So I'm going to go up 3, about right there, to the right 3, down 3, and to the left 3. And then I'm going to connect the dots as best you can to draw a circle. Okay, so center at x3, y0 with the radius of 3. Describe in part A how you would use the graph of the relation to draw the graph of the inverse. Well, graphically, you could reflect the graph in the line y equals x. Okay, so if you're drawing your line y equals x, it goes through all the points which have x equal to y, which would be 0, 0, 1, 1, 2, 2, and so on. So we get this dotted line up here, and then I can just visually look and reflect it over the line. I'm going to grab a pen here so we can see the difference between them. I see that this little portion is going to be reflected here. Okay. And then if I was thinking about where the center might go, I could judge the distance from the line, or I could change a point. So here I'm seeing 6, 0 would become 0, 6. Okay, here 0, 0 would stay 0, 0. Here, that's 3, -3 would become -3, 3. So I can kind of see the outline now to help me sketch the rest of my graph, which is going to go through like that. Okay. So the original function is in the pencil, the inverse is in the red pen. So we've sketched both the original and the inverse on the graph, on the grid. Describe how to use the equation of the relation to determine the equation of the inverse. Okay, when we said when we're doing it algebraically, we need to switch x and y and solve for y. Okay. So determine the equation of the inverse in this form: x minus h squared plus y minus k squared equals r squared. Now it's just a really fancy way of matching what is up here, where we see x with the squared, y with the squared, and some whole number on the other side, which happens to be a perfect square with 9 there. So we're going to do the same thing. We're taking this equation up here, switching x and y. So I'm going to switch in the first brackets there where there was an x, I'm going to put a y squared plus where the y was, I'm going to put x squared, and that's equal to 9. Okay, and I'm just going to match their notation here to say that they wanted x first, so x squared plus y minus 3 squared is equal to, and then r squared, interchange 9, and write it as a perfect square, 3 squared. Okay, so this matches the form of the equation of the circle. Could we write the equation in terms of y to verify a sketch on the graphing calculator? So we're going to take this right here, and we're going to try and solve for y. And I notice first I want to get this term with y alone, so I'm going to take x squared to the other side. So I would have 3 squared minus x squared equal to y minus 3 squared. So I've taken x squared to the other side here by taking it away. Okay. In order to get y alone, I first have to get rid of the square, so I have to square root. And I'm going to switch back instead of 3 squared to make it a little bit neater. I'm just going to go 9 minus x squared, taking the square root of that side. On the other side, I would take the square root of y minus 3 squared, and taking the square root of the square would just leave me with y minus 3. Last step to get y alone would be to add 3. So root 9 minus x squared plus 3 is equal to y. And I should extend that there, the radical symbol, to show me that 9 minus x squared is all under the root symbol. And then you could graph this, and you would need both the plus and minus root, okay? And you would see both halves of the circle. It would graph it there for you. Using interval notation, state the domain and range of the relation and the domain and range of the inverse. Okay, let's look at the pencil first. I'm going to write original here. Okay, the domain in interval notation, or those bracket notations, would go from 0 to 6 on the x. So we're limited there. 0 to 6 can be equal to 0, so I'm going to square bracket, can be equal to 6, square bracket. The range goes from -3 to +3. And if this was to agree with what we had set up top, we would say that the inverse would have the domain that was the range of the original, so I'd expect -3, +3 here for the domain, and I would expect 0, 6 to go down to the range. And let's just verify that. The inverse, the domain, see, x starts here, stops here. -3 to 3, which matches. And the range starting at 0, going up to 6, which does match the domain there. So we can see the range became the domain, and the domain became the range. Okay. How would we use function notation to write an inverse? So we're starting to learn that a lot of these operations that they're putting on the functions tend to have special symbols that go with them, and it's true as well for the inverse of a function. So if a function has an inverse, which is also a function, there's the key point there, meaning if it's not a function, then you can't use the symbol, then f inverse x would be written as f with a little -1. Now, do not confuse this with an exponent. It is not an exponent. It does not mean the reciprocal. And when I mean it does not mean the reciprocal, I like the example they used down here. They said if 10 to the -1, if the exponent -1 is 1 over 10, that's true, but the f to -1x is not the reciprocal function, okay? This is the function that takes all your y values, takes the reciprocal of them, 1 over y. This is the function that is the inverse, takes your y values, switches them with x. Not the same, doesn't mean the reciprocal, it means the inverse. And we'll just have to memorize that. Okay? So what do we do here if we're trying to write the inverse function? We'd follow a similar process that we've been using algebraically. In most cases, if we see an f of x, we know that that's equivalent to y, so we're just going to replace it to y, so that then we can switch x and y, solve for y, and then we can replace y with the inverse. So it's kind of an extra step, step 1 and step 4 are extra onto what we have been doing previously. So if we go down to class example 2 here, f of x equals 2x minus 3, we would first replace f of x with y, so that y is equal to 2x minus 3. Then we would switch x and y. So now I have x equals 2y minus 3. Solve for y. Add 3 on both sides. So I'd have x plus 3, or isolate y to 2y equal to 2y. Divide by 2. I would have y equal to x plus 3 all over 2. And then, because I'm stating that this is an inverse function, I'm going to replace y with the inverse notation that says f inverse of x, which is the inverse of this f of x, is x plus 3 all over 2. Okay, then we are done. We've written the inverse using the function notation. Okay, try this one as well. Same steps, following steps 1 through 4 up here. Replace f of x with y. So instead of f of x, now it says y equals x cubed plus 4, which is a little more relatable for us. Then we switch x and y. So x equals y cubed plus 4. We have to try to isolate y, get it alone. So we're going to have to take away 4 here. X minus 4 equal to y cubed. We have to get rid of the cube because we just want one y. So we're going to have to take the cube root of x minus 4. That's equal to y. And to finish the problem and use the proper notation, we're going to replace y with f inverse of x. So f inverse x is equal to cubed root x minus 4. Okay. So please note, anytime you guys can stop this video and you can go back, you can slow down, you can ask each other questions. That's what it's meant for. And we go up to the top here, page 53. Consider the function x squared minus 4. Graph it on the grid provided and state the domain and range. Okay, the x squared graph with the constant term 4, the negative 4 is my y-intercept, and they're going down by 2 here, so 2 squares down, I put the y-intercept. Then I'm just going to use a couple numbers to try and get the shape of my graph. So let's go, I don't know, 2x is, when x is 2, 2 squared minus 4 would be 4 minus 4, or 0. And the same would be true of negative 2, because negative 2 squared is equal to 2 squared. And then let's try 4. 4 squared minus 4 would be 16 minus 4, which would be 12. So when x is 4, y is 12. Same is true for negative 4. And we're expecting the parabola shape that would associate this graph with a quadratic, the x squared. And we can go like that. Just draw some arrows on that. Show that it's going up and forever towards the top of the page. Okay, so determine or state the domain and range of this graph. It's quadratic. I see a parabola. I could assume it's always going to go forever to the left and right. There, it's not going to stop. So I would say the domain is xcr, or any real number. X is an element of the real numbers. The range, my lowest point is negative 4. So I would say y has to be greater than or equal to negative 4. but it can be any real number as long as that number is above -4. Determine x equals f of y and solve for y. They haven't introduced us to this notation formally yet, but we can see if y was supposed to equal f of x, let's just write that up above it so we can compare. If y was supposed to equal f of x, they've switched x and y on us, which means find the inverse or determine the inverse and solve for y. So switch x and y, solve for y. So we are going to take this equation. We replace f of x with y. Then we're going to switch x and y so that x is equal to y squared minus 4. I'm going to add 4 to each side to isolate y. And then I'm going to take the square root. Now, to get the full inverse, I'm going to have to take the positive and the negative square root equal to y. And I'm going to show you why in a second here. Graph the inverse on the grid and provide it and state the domain and range. So if you were to enter this on your calculator, you would have to go y1 equal to root x plus 4. And then you would have to go y2 equal to the root, or negative in front of that one, x plus 4. And you would get two graphs that take on two shapes. So the positive root would draw the top half of this graph, and the negative root would draw the bottom half of that graph. Okay, so state the domain and range. Now I don't even have to study this graph all that extensively to know the domain and range because I had my domain and range of the original. So I could switch them. So I could say the domain of the inverse was the range of the original. So I could say x greater than or equal to -4, xer, or x an element of the reals. And the original domain was xer, so the new range of the inverse would be yer. And this would match our picture because we're starting at 4, and all of our x values are greater than or equal to 4 to the right of 4. And then our y values, this is going to go up gradually, and this is going to go down gradually forever. So we would say y is any real number. So this is asking us, is the inverse f a function? In other words, test with the vertical line test. Drag a pencil, paper, whatever it is, across this function and see that it never crosses twice. And I can see the double cross there. One x value has two different y values. So this inverse is not a function. Okay, and that leads us to why they're using this notation. They would not use the f with the little -1 notation because that implies that it's a function. And since it's not a function, they're going to switch to other notation, which just tells you to switch x and y. Still the inverse, just not a function. How could the domain or range be restricted so that the inverse of f is also a function? So how could we, in other words, find a way to limit either the domain or the range of this graph so that we essentially would have a function that when we dragged a vertical line across it, it would cross only once. And the only way to do that is to get only half of the parabola, or half of this sideways parabola, I should say. So I would either just the top or either just the bottom, which means I could set the range to be y greater than or equal to 0. Then that would give me only the half. That would cut out that whole bottom half. Or I could say only y is less than or equal to 0, and that would give me the bottom half. But I have to think about how could I restrict the domain or range of the original. Now, if I'm cutting the range of the inverse, so I was saying, okay, I'm going to limit y on the inverse. I'm going to say either y is greater than 0 or y is less than 0. I know that the range of the inverse relates to the domain of the original. So I have to think about cutting this graph in half. So I could say either y is less than or equal, or sorry, x is less than or equal to 0, or x is greater than or equal to 0, and that would either give me the left half of this graph, which would correspond to the top, the bottom, or I could take this part of the graph, and that would correspond to the top. So I could restrict the domain of f, domain of the original, to be y greater than or equal to 0 or y less than or equal to 0, and I would have a function, or an inverse that was also a function. Okay, so we just have to think, where is the center point of that quadratic? Cut it right in half, take half of it, your choice, and then the inverse would be a function. Okay, all right, I'm going to tell you right now, I like this question, and I will likely put it on the test in the future. So let's make sure we know how to do this one. And talking about when we are determining the inverse of a function, we can get an equation. So we do the whole xy thing, we switch, we solve for y, and then we graph it. And it says in this case he graphed and he got a parabola. Why is Don's equation of the inverse not complete? And why the graph in the correct inverse is not a parabola. Okay, so I'm going to go up here, and we're going to sort of trace Don's steps in trying to graph this function and its inverse. So here's the function, y equals root x minus 3. If you want to quickly plot this in your graphing calculator, I'm going to go ahead and draw it, because we know that x has to be greater than or equal to 3 so that we're not taking the square root of a negative, and it's going to go that way as a square root graph would, in which there is no negative sign out front, so I'm just assuming the positive root. So it's going to start at 3 and general shape go to the right there. Now we want to switch x and y, and then we're working to solve for y in order to consider Don's inverse equation that he wrote there. So first, to get rid of the square root, I have to square x. And when I square the square root, I'm just left with y minus 3. I'm going to add 3 to both sides. So I will have y equal to x squared plus 3. Well, okay, that's what Don got. But he graphed the inverse, and he obtained a parabola. So what would have happened was he would have graphed this in his calculator, and he would have got something like that. Okay, this is not correct. So the equation, it is complete, however it's missing sort of a extra statement there, and why the correct inverse would not be a parabola. This goes back to the last question, where if I'm going to have half of this graph, right, not the negative root, I just have the positive root, I should only have half of this graph. Okay, so let's think about our domain of our original. Okay, the domain of the original was x such that x has to be greater than or equal to 3. Okay, domain of the original, x such that x has to be greater than or equal to 3, XCR, and to practice, let's write the range of the original too. So the range of the original was y greater than or equal to 0, YR, because this graph stays above the x-axis. Now, if this is our domain and our range of the original, that should influence our domain and range of this graph. So let's go the domain of the inverse. The domain of the inverse should be the range, except we write it in terms of domain with x. So x greater than or equal to 0, XCR, or x an element of the reals. The range of the inverse should be y such that y is greater than or equal to 3. Y is an element of the reals. Now if we compare this domain and range, the characteristics of our inverse to our characteristics of this parabola that Don drew, we can see that he got the range right. It's greater than or equal to 3, but the domain was not. By stating a domain x greater than or equal to 0, we'd cut this parabola in half and only take this part. So in reality, his graph should look like that. That eraser is terrible. Okay, but get the point. It should have started at 0 for x and headed towards the right. It should have been only part of his parabola. So explain why Don's equation is not complete. Don's equation is not complete because he did not consider restrictions on domain and range. The correct graph is not a parabola because when you consider the restrictions, it's half a parabola. The correct graph, that's the most mathematic way I can think of say that, is that it's half a parabola. I don't know what the correct name of that would be. Okay, so by solving or verifying the equation, stating some domains and ranges, maybe making me a nice little explanation. Again, you got the star beside the question. Maybe draw a picture. That would be full marks for a question like this. Explaining where the restrictions were coming from, what the graph should look like. All right, so hint, hint, study that one. Okay, verifying that functions are inverses of one another. So it says determine f, that's a composition sign, f composition or f of f inverse x and f inverse of fx for class example number 2a, where f of x was 2x minus 3. I'm going to pull up class example number 2a for a second. Here it was. Class example number 2a, f of x, I'm just going to copy that down. F of x was 2x minus 3, and f inverse x was x plus 3 over 2. All right. Okay, now that I have that, I can go ahead with this question and do the composition. So this, I'm going to start with this one first. The f of f inverse x means I am taking the function f and plugging in the inverse function into it. I'm going f of f inverse, so this is f inverse is x plus 3 over 2. Okay, so I'm plugging x plus 3 over 2 anywhere where there is x in this equation. So I'm going to 2x plus 3 over 2 minus 3, so just where I see x, I don't include that negative 3 or anything. And then we could say that we are going to cancel the 2's. 2 divided by 2 is 1. I'd have x plus 3 minus 3, or I would just have x. Okay, so the composition f inverse x is just x. Now, let's try the composition here and see if we get something different. So this one is the composition of f inverse of f of x, okay, where we have the inverse function. We're going to plug in the original function f of x, which means I'm going to look at the inverse function, plug in 2x minus 3. So I'm plugging in 2x minus 3 anywhere where I see x in this inverse equation. So equal to, I see an x plus 3, so instead I have 2x minus 3 plus 3 divided by 2. So I'd have 2x minus 3 plus 3. I'd really have 2x over 2 because the minus 3 and plus 3 would go to 0. 2x over 2 is just x. So what do you notice? Both of these values, or both of the simplifications, turned out to be x, which happens to be our mirror line, y equals x. But we could say two functions f and g are inverses of each other if their composition equals x, and if you reverse the composition, g of f, so f of g and g of f are both equal to x. All right, so that took about half an hour. You guys have the remaining time to work on your assignment. You should have time to finish the assignment. Bring any questions that you have about the homework to class tomorrow so that we can review them, do a little bit of studying, a quiz on lessons 6 and 7 tomorrow in class. All right, I'll see you on Friday.